Courtney, if you could share your screen with us, please. Wonderful. Good afternoon, everyone, and thank you for attending today's webinar on incorporating the forgotten thermal benefits of brick with BIA's Managing Senior Engineer, Courtney Fried. We are thrilled to be hosting such a prestigious organization in our community today. My name is Brian Yansak, and I'm the Design Studio and Events Coordinator for Glen-Gery. During the presentation, you will notice the Q&A function at the bottom of your screen. Please feel free to submit any questions throughout the presentation, and they will be answered at its conclusion. Your attendance will be marked, and we ask that you stay on for the duration of the course to receive the credit. Everyone attending the duration of the course will be receiving a certificate of completion by early next week, and those who provided their AIA number during registration will be submitted for AIA credit as well. If you are participating today but did not register beforehand with your information, please email events@glengery.com. That is events@glengery.com with your information, and I will be happy to make that happen for you. Today's session is also being recorded, and a link for you to access it will be provided within your certificate of completion. I would now like to introduce our speaker today, Courtney Fried. Courtney currently serves as Managing Senior Engineer in the Engineering and Research Department of the Brick Industry Association, where she develops documents such as technical notes, participates in codes and standards activities, as well as answers technical questions from architects, engineers, owners, and contractors. Prior to joining BIA in 2017, Courtney worked as a forensic consulting engineer for over 15 years, investigating and repairing various types of architectural and structural problems in existing buildings, with a focus on masonry of all types, ranging from history brick, mass masonry, to modern brick, cavity and veneer wall construction. In addition to brick masonry, her projects involved materials such as structural clay tile, dimension stone, concrete, steel, and wood timber, with these other materials typically occurring in combination with brick masonry. Courtney is a licensed professional engineer in the state of Virginia. She earned her Bachelor of Civil Engineering degree from the Georgia Institute of Technology and a Master of Science in Civil Engineering with an emphasis in structural engineering from Stanford University. And with that, I would like to now turn it over to Courtney. Courtney,
sorry,
you may
I
be
was
on
muted.
mute.
I was muted. Apologies there. Welcome, everybody. Today, we're going to be talking about incorporating the forgotten thermal benefits of brick masonry. So before we get started, just a quick reminder that BIA can provide a lot of assistance for design professionals. Hopefully you're familiar with our technical publications, the technical notes for brick construction. Those are available on our website. We also receive questions from design professionals and can provide answers to those. And we can also do limited reviews of brick masonry details and specifications to help you get over humps in your design process. So just reach out to us at our website, gobrick.com, and we're happy to assist. Now, in this particular case, BIA is a registered provider, but Glen-Gery is going to be taking care of all your continuing education for this seminar. Here are our learning objectives. They're a little dense, I'll let you read them, but we'll skip ahead and focus on the content of what we're going to cover today. So here's an outline. We've got a lot of content to cover. First, we're going to start with a little history of both the energy code and historic construction. And then we're going to move into some basic concepts about energy and the current energy codes. And then we're going to just discuss the findings of the research conducted by the National Brick Research Center and close with the ways that this information from the research can be incorporated into projects. So first, let's talk about the reasons why you as an architect might choose brick for cladding. Feel free to type stuff in the question and answer box, and we'll see how they match with the answers that we typically get here on the screen. First and foremost, we have tried and true historic performance. The building pictured here is a great example of that. This is the oldest brick building in the United States, and it's from 1665 and still in good condition. I think it's a national monument of sorts, so it's not currently a residence, but still functional. Obviously, aesthetics, that's what's cared about. I see an answer for durability and longevity. Yes, that's our historic performance, along with our resistance to certain hazards like fire and impact. Additionally, we have reduced maintenance compared to other materials. And then if there are any other ones, so I like the one about durability too. Here are just some examples of those in action. Now, you may notice that energy efficiency isn't usually mentioned on that list. So if one of the primary goals of your project is energy efficiency, is brick or masonry in general one of the systems on your short list? If not, why not? It should be on the short list, because if you're treating brick as 4 inches of paint, you are missing out on a lot of performance in your opaque wall assembly. And so the point of this presentation is to talk about how we reclaim that performance. Energy efficiency is a relatively recent addition to the codes and standards that we use to design and construct buildings. The development was based on the oil crisis in the 1970s. It spurred the country into action in order to create a national building code related to energy efficiency. While that crisis has passed, obviously climate change has come to take its place. So energy efficiency is still a really important concern for us. Even though we've had a lot of improvements since the 1970s with regard to building construction, buildings still use a really large percentage of energy that needs to be better controlled. Now, some of that increase in energy usage is due to the changes and the increase in the way that we use electronic devices. So, our engineering friends over in the electrical and the mechanical world have a big role to play. But from our perspective, and for this discussion, we're going to talk about the building envelope. So these graphs are based on data from 2019, and you can see that energy usage in the United States is pretty well distributed throughout our sectors here. However, this blue wedge here is actually the losses that are inherent in our electrical distribution center system. So when those get redistributed appropriately to our various sectors, buildings end up using more like 39% of the total energy used. Now, when we split that out and look at the division between commercial and residential buildings, they're relatively evenly split, with residential having a slight increase in energy usage. As we dig deeper into the way energy is used in buildings, we can see that it is our building envelope is our largest contributor to energy usage. And so digging to within that envelope, both our opaque wall and our windows contribute. But the proportions in which they contribute depend on what climate you're in. So in cooler areas where your heating loads are more critical, you have very cold winters, your opaque wall performance is going to be pretty evenly split with your window performance, which here is separated between the thermal performance of the window itself and your window wall ratio, which is our proportion of windows to opaque wall. Now, if you're in a warmer climate, that flips considerably in that our opaque wall is now this tiny sliver of contribution to our energy use, and it's really the window performance and that proportion of our windows which is really going to dominate our energy usage. Now, in some place that's kind of middle of the road, for instance, I'm outside Washington, D.C., our heating and cooling loads are pretty balanced. So it's not going to be as extreme as this, but you would still use the same concepts of balancing the proportions of opaque wall to window and focusing on our window performance to get overall good envelope thermal performance. A study from the Urban Green Council, which is the New York chapter of the US GBC, they found that that modern commercial and large-scale residential buildings don't significantly perform much better than our mass masonry buildings from the 19th century, which is pretty crazy to think about. Unfortunately, what we think has happened is that even though our knowledge base for building construction and techniques grew, it also created the potential for loopholes, such as wide expanses of curtain wall glass. So it's pretty well understood that even high performance glass is a pretty poor insulator compared to opaque wall assemblies. As a result, there's normally a lot of pressure to stuff even more insulation into our opaque wall to compensate for that known lack of performance in the glass. As we can see here, though, that concept isn't very effective. This yellow line, which is a wall with R20 in the opaque sections, pretty greatly outperforms a wall with R40 in the opaque sections, no matter what your window wall ratio is, solely because of the difference in performance of the window itself. You really want to make sure that the thermal performance of that window is going to give you huge increase in performance, and it's going to allow your opaque wall to do what it needs to do and really maximize the performance that you have out of your opaque wall. Now, I'm sure if you've ever broached that topic before with clients or tenants, you've received pretty strong pushback. Typically, people assert that as much glass as possible is needed to achieve daylighting and views. So here we have an example of a case where the view is not sacrificed by adding a portion of opaque wall and avoiding full height window wall. In some respects, some people would argue that the view is actually improved because you don't see the crap on the roof of the lower building. You also don't need to have those floor-to-ceiling windows for effective daylighting. You really don't get any benefit from daylighting for windows near the floor of a building, and it's really the combination of the window kind of in this high mid zone along with a shading and redirection device that really gets that sunlight into the area where it's going to be most effective. So before HVAC systems were incorporated into buildings, designers had a number of different strategies to provide occupant comfort. So we're going to discuss a few of these in our brief history of wall construction. One of our oldest building materials is adobe, and which consists of blocks or layers of mud that have been baked in the sun. It's a pretty iconic kind of building material for the desert Southwest here in the US. And these really thick, heavy walls help to protect from the desert heat during the day. And then it released it to the interior at night when the exterior temperatures fell pretty significantly. When fired clay became common, it was used to create similar structures to adobe with a few differences. Because brick are fired clay, they're more durable. So they could be used to construct taller walls, those that provided structural support for multiple levels, and it could be used throughout the United States where it had more exposure to moisture. These walls manage moisture like a reservoir, absorbing the moisture from the rain and then slowly releasing it after the event is over. It manages heat in the same way, that same reservoir concept, where the heat on the outside of the wall gets absorbed and stored in the masonry and released later when the temperatures on the outside changed. Our brick walls evolved to include drainage cavities so that our moisture management was no longer limited to the reservoir capacity, but these walls maintained the mass and structural capability of their solid predecessors, and they managed heat much in the same way through that reservoir concept, though we do get some added benefit from the inclusion of an airspace. On a smaller scale, we have fireplaces. Before conditioned air, these were relied on as the primary source of heat. They were often pretty substantial in size and typically consisted of brick or stone masonry. Now, obviously, they were made out of these materials because they were durable and resistant to fire, but they also absorbed the heat from the fire and could reflect it out into the room even for a period of time after the fire was extinguished. In a more modern application of this principle, we have passive solar heating, which was a popular concept in the 1960s, 1970s. So in this case, we have sunlight from the winter sun going through south-facing glass, and it gets absorbed by exposed brick walls and floors at the home interior, and then that heat is later released into the room when it gets cooler outside. In the southern United States, design and planning of structures had to incorporate a variety of strategies, including the principles of heat flow, in order to create occupant comfort in a very hot and humid climate. So first, when possible, they used east-west building orientation and the shade of trees to reduce direct sun exposure. However, even with trees present, they incorporated additional shelter through the large wraparound porches and deep eaves. Symmetric placement of windows and doors allowed for cross ventilation to occur. And then in the rooms themselves, we had high ceilings that allowed the hot air to rise away from the occupants. And that was combined with the use of triple hung windows that could be cracked at both the top and the bottom, at the top to allow that hot air to escape, and at the bottom to allow cooler air and breezes to enter the room. These principles of heat flow were incorporated into a large scale in the U.S. Pension Bureau building, which is now the National Building Museum in Washington, D.C. There were openings under each window that allowed fresh air to enter the building and circulate, while the hot air that resulted ended up escaping through the central atrium and the clerestory windows at the roof level. Our modern building designs rely much less on these strategies because we have HVAC systems, but we don't need to ignore the potential benefits of these strategies. Hopefully, as we continue, you will see that these concepts reoccur in different forms. So now let's talk a little bit about basic principles that come into play when we discuss energy. First and foremost, we have heat transfer. There's three methods of heat transfer. We have conduction, which is heat passing through a material. We have convection, which is heat flowing through air currents. And then we have radiation, which is heat flow emanating from a material. You usually have a combination of all three of these in any given situation, but the proportions of those vary depending on the situation. No matter what type of heat flow method is present, the direction of your movement is always from hot to cold. In addition to heat, we also care about water. Water can take multiple forms. Normally in buildings, we're mostly concerned about its liquid form, but it can also give us some pretty serious issues when it's in gaseous form, so we need to be aware of it. Two major ways that water vapor gets through our wall assembly: diffusion, which is it passing through the pores of our material, and then we have air leakage, which is when our air currents carry water vapors through any gaps or penetrations in the layers in the wall assembly, and we generally refer to that as moisture-laden air. We care about this is because of the potential of condensation. In a technical sense, condensation occurs when your air is cooled to a point where it's fully saturated and it can't carry any more moisture. And so it condenses. This temperature is called the dew point. Everybody should be pretty familiar with the experience with holding an icy drink on a hot summer day where that warm, humid air comes in contact with the cold side of the glass, and all the water vapor is released and it turns into the droplets that run down the side of your glass. Now, because of this, we need to design our wall assemblies so that either condensation will not occur within our wall assembly, or that if it does, it's going to occur within the wet zone of our wall assembly where it can be managed. So what happens if we don't pay attention to this? Well, there's a bunch of things. First of all, you can get water leakage at the interior. You can have a loss of insulation value because wet batt insulation does not perform as it was intended to. And then that can also lead to microbial growth. So hygrothermal modeling is something that's recommended to help you identify cases in which condensation outside of the wet zone could occur and how to avoid them. A thermal bridge is an element that has a higher thermal conductivity than the surrounding materials. So it creates a path of least resistance to heat transfer. I hope everyone's pretty familiar with the example of a steel stud backing without continuous insulation. That high thermal conductivity of the steel allows heat to short circuit the insulation that's in between the studs. And so we've got a loss of performance in that situation. And then even worse, if that stud surface is cold, we can get condensation on it. And that's usually located in the dry zone of our wall assembly. As noted here in the orange box, the thermal bridging results in a pretty significant loss of performance in our batt insulation, going from R19 to about R7. You need continuous insulation outboard of that stud framing in order to mitigate the thermal bridging effect. R value is a term that's pretty commonly used and understood by everyone in the AEC industry and even homeowners. It's basically our primary measurement for the resistance of heat flow through a material. And the larger that number is, the greater the resistance to heat flow. But let's delve a little bit deeper into what R value really represents. While the basic principle of hot moving to cold always applies, this flow is actually three-dimensional, spreading out in all directions. As you're aware, though, we're often not able to look at problems in 3 dimensions because they're too complex, and we don't always have the tools or the capabilities to look at it in 3 dimensions. As a result, we've got to simplify the behavior to make it more manageable and understandable. In the case of R value, we take our complex 3D heat flow problem and reduce it to a one-dimensional problem. The test for determining R value is ASTM-C 518, and in that procedure we have a hot plate on one side of a material and a cold plate on the other. And hot moving to cold, that sets up a heat flow through the material from the hot plate to the cold plate. The resistance to heat flow, as measured in this test, determines the R value. Now, R value is considered steady state property of the material because the temperature of this hot plate stays constant throughout the test. Now, this level by simplifying this problem to one dimension, we're measuring what we have the ability to measure, even though it's really only a snapshot of the behavior and it may be missing information. Fortunately, the situation is not inert. As our tools improve, our ability to obtain more information also increases. One of the tool improvements that we've seen over the years is energy modeling software. However, even with these new tools, a lot of talk about energy efficiency generally maintains the simplification and reduces everything to R value comparisons. As with all simplifications, some information is lost. Now, this isn't a major concern for most building materials, but it is for masonry and concrete. And why is that? That is because of thermal mass. Thermal mass is a unique characteristic of materials like masonry and concrete in that they slowly absorb heat and they hold on to it, acting like a reservoir, the way we talked about in the historic wall construction. Once full, these materials also slowly release heat over time. So the effects of thermal mass are depicted in this graphic. The blue line represents the exterior temperatures during the day and night. And then the orange line represents the variation in temperature in the airspace behind anchored brick veneer. So that's going to approximate the maximum and the minimum your interior temperatures are going to reach. So as you can see, your range of temperatures at the interior are going to be more stable with less variation. And then, so that obviously improves occupant comfort, and it also reduces the amount of heat that reaches the interior and the amount of work that your HVAC system needs to do. Now, the peak temperature, the time of the peak temperature on the inside of the building also comes later than it does on the outside. We refer to this as the lag. This resulting lag shifts your demand from heating and cooling to a later time of day. So if R value doesn't capture our benefits of thermal mass, how exactly do we assess them? As of now, the best tool that we have available is called a guarded hot box. Over the past few years, the National Brick Research Center, known as the NBRC, has conducted research into the energy efficiency of brick wall assemblies. So to do so, they used a hot box, which is an accepted method of determining thermal resistance, but they supplemented the measurement elements in the apparatus to allow for more documentation of the behavior of thermal mass. So here we have a diagram and photos of the hot box apparatus at the NBRC. So here on the left is the actual apparatus viewed from the side. You can see from the scale of our researcher, Nate, here, both chambers are pretty large. They're about room sized on their own. This one here on the left represents the climate or the exterior temperatures. Here, this chamber, the metering one, represents the interior temperatures on the inside of the building. And then in between, we put our wall specimen. They were full-size wall specimens ranging about 6 feet tall and 8.5 feet wide. They were full-size, built on site for incorporation into the research testing. So on the left, we have an example here of the brick veneer on CMU under construction. And then here we have on the right, we have an example of a cold form steel stud wall with continuous insulation. And you can see here, they used a combination of sensors, both on the studs and in the field in between, in order to document the differences in performance. And then you can also see that we have these circles represent the one part of our two-part brick tie, and those are always installed aligned with our studs. So each specimen was subjected to the same series of temperature changes, but they were applied in two distinct patterns. The first pattern was a series of static temperature changes with a set difference between the climactic and the metering chambers, which also included cases where the exterior was warmer than the interior, and also cases where the interior was warmer than the exterior. The second pattern is called a Sol air cycle. It's a standard temperature cycle, and it represents the range in temperatures from the low to the high in a given day. And so that variation in temperature creates a dynamic loading for our test. And you can see each one of these peaks and valleys is a single 24-hour day period. And they had about 5 of them. 5 days worth. So later we're going to discuss the results of the NBRC testing, but first let's talk a little bit about the energy code and its provisions, because it's going to relate to our findings. There are 2 code documents that we use for energy efficiency in both commercial and large-scale residential buildings. We've got the IECC, the International Energy Conservation Code, and ASHRAE 90.1. The IECC is our model code, which gets adopted by jurisdiction, while 90.1 is simply a standard. However, they are interrelated, with 90.1 serving as one of the permitted compliance paths in the IECC. The energy code requirements are structured around the location of your project and the associated climate in that area. The country is divided into 8 large climate zones, and then subdivided based on the kind of moisture present in your particular climate. Here's a diagram that depicts the various compliance paths that we have in order to comply with the IECC. So the first row here are those that are explicitly listed in the IECC. But as I mentioned, you have a choice to use 90.1. And so if you do so, the 90.1 also has a series of options that are generally consistent with what your options are in the IECC. In both cases, you have a lot of options for compliance, ranging from something that's very straightforward and prescriptive, not complex, to something that reaches near full simulation of the energy in your building, which gives you the most flexibility, but it comes with more complexity. Another standard that is specific to concrete and masonry is a joint standard developed by the American Concrete Institute and the Masonry Society, ACI TMS 122. It provides information about the thermal properties of concrete and masonry assemblies to be incorporated in things like energy models or ComCheck or things like that. It's currently undergoing a pretty significant expansion to become 3 new standards that will include content for clay brick veneer specifically based on the recent NBRC research. Once these are completed, they'll be adopted into the IECC by reference. Here we have an excerpt from the IECC. This is the simplest option you have for compliance, which is the R value. This option only considers the contribution of your insulation in the wall, and all other components are ignored. The requirements are going to differ based on your wall construction type and your climate zone. You do have a couple options when you're working with stud walls. Depending on the depth of your wall, you can do all insulation. Otherwise, you have a combination of insulation between your studs and continuous insulation. As you can see, our mass walls have a much lower requirement than our framed walls, and that's how the code recognizes the thermal mass that's present in mass walls. Another one of the prescriptive methods to comply with the energy code is the U-factor method. If you recall from our diagram, we are moving one step to the right on our compliance path options. So this one's a little bit more complex, but it's still prescriptive. But the benefit that it gives you is that you have a little bit more flexibility. In this case, you're not just looking at the insulation, you're looking at the contribution of all your layers in your wall assembly. And that can be helpful, especially when you have masonry involved. You have a similar difference between frame wall and mass walls. And again, this is how the code is simply accounting for thermal mass in our mass walls. Based on precedent, when a wall assembly incorporates brick veneer over frame or stud walls, the requirements for frame walls must be used. This is because energy experts have argued essentially 3 reasons why we have to do this. One is that the heat capacity of a masonry veneer is too low. 2, that the vented airspace behind that brick veneer undermines the thermal performance of that brick veneer. And then the 3rd is that those ties are thermal bridges, and so it degrades the thermal performance of the veneer. However, load-bearing brickwork, which we can see an example here on the left, is generally 5 to 6 inches thick, and it's not necessarily fully grouted. So that would generally qualify as a mass wall, but in terms of weight or size, it's not really that much different from our 4-inch brick veneer. So it did make us wonder whether or not the arguments used to force brick veneer into the frame wall category, whether or not those reasons were valid. First, let's talk about heat capacity. Heat capacity is a characteristic that describes the amount of energy needed to raise the temperature of a material. So as a result, a larger value of heat capacity equals more thermal mass. In energy codes, our designation of mass wall versus frame wall is partly based on that heat capacity. So you could have a situation where you do have thermal mass, but it doesn't meet the thresholds in the code, and you would have to use the requirement for frame walls. These requirements do differ between IECC and 90.1. 90.1 makes the determination of a mass wall only through heat capacity. IECC has that same requirement based on heat capacity, but also gives you options based on the weight of your wall. In a strict reading of the code, an anchored brick veneer may be able to meet some of these qualifications for mass walls, even though they haven't historically been permitted to in the past. And the reason we say that, here's an example calculation using published information from ASHRAE Handbook of Fundamentals and ASTM information about standard dimensions for brick face veneer. So based on our 4-inch nominal unit with, the amount of voids we're allowed to have, and assuming a density at that limit, we do end up with a heat capacity over 5. And so that would argue, that makes the argument that the heat capacity of anchored brick veneer is large enough to meet the requirement for mass wall. And this is a very simple calculation. We didn't even include any of the mortar. The findings of the MBRC research will further help determine whether or not those assumptions about brick veneer wall assemblies are valid. So here we just talked about a simple calculation based on published information. Here we have some results based on a tested heat capacity value that was performed in the hot box. So we call this an apparent heat capacity because it's a little bit different than the calculations that were done, because we're working with the entire wall assembly that doesn't consist of the same materials. So it's slightly different. As you can see, the lowest value of a wall assembly that had brick veneer on it was just under 10, while as the wall assemblies that did not incorporate brick veneer were much lower, not even exceeding 2.5. Now, while we can't directly compare these numbers to the thresholds in the code, it does give us a good demonstration that the order of magnitude of our heat capacity of that entire wall assembly is consistent with a mass wall compared to a frame wall. Now, that second argument to justify not being able to use the thermal performance of our brick veneer was about the airspace behind the brick. The argument is because that airspace is vented, we get circulation of air behind that brick, or convection, and that's going to degrade the thermal performance. So the researchers at MBRC did two things. They did testing in the hot box to evaluate this, and they also did some fluid dynamics modeling. What they found was pretty interesting is that, of our 3 methods of heat transfer that are possible, radiation dominated in the performance of brick veneer. So if we had 80% of our heat flow crossing our cavity through radiation, that meant a lot less available to occur through convection. And so that meant it didn't match the assumptions, and you don't get a degradation because of circulation of air behind the brick. Now here we have the results of the hot box testing for the same thing. Now, to bracket the potential range of performance, 2 different veneer assemblies were tested. The first one here that says closed weeps, they completely covered up the weeps that were present at the bottom of the wall to prevent any air from entering. And then the one here that says open weeps wasn't just the open weeps at the bottom, they also incorporated an opening at the top, but not even consistent weeps at the top. They literally removed the entire top course of masonry in order to get maximum airflow through that cavity. And as we can see from the results, the tested R value in the hot box is pretty equivalent. We really don't see a difference, and that helps to support the argument that radiation is so dominant, we don't lose performance through convection. Because of that dominance of radiation, MBRC also investigated how variations in that airspace could change thermal performance. And so obviously it was found that by increasing the reflectiveness of that cavity surface, you can redirect some of that radiant energy back out towards the exterior and stop it from getting to the interior of your building. So the incorporation of this radiant barrier or reflective insulation, they found could increase the R value of the wall by as much as 1.6. Now we do keep in mind that the permeability of those materials is quite different, and so you do need to consider whether or not they're appropriate for your wall assembly and your climate zone. Now, the last of the supposed justifications for treating brick veneer walls differently from other masonry wall assemblies is that the veneer ties act as thermal bridges that degrade the performance. So, through the use of an IR camera that was incorporated into the hot box, they did not find any evidence of temperature variations that were suggestive of thermal bridges due to the ties. And you can see here there's an arrow pointing to the space where they knew the tie was behind. We can see temperature variations at our bond line between our brick and our mortar, but we don't really see anything at all due to the brick. So one of the reasons why we think that is the case, not only do we have a size differential in play, brick veneer ties, as you can see down here in the bottom right, we're generally talking about wires, small size plates. The size of those steel elements in comparison to our brick masonry is vastly different. So, and then you add to it the fact that our masonry is acting like a heat sink. It's going to slowly absorb any heat from the tie and be slow about reducing it. And then in the same way, any heat that's transferred to the brick is going to be slow to get into the tie. So from our perspective, we've concluded that they don't act as thermal bridges. But we do understand you may have either, a code official or a facade consultant or an energy consultant who is not willing to accept that. So there's other methods that you can use. Obviously, stainless steel is a good option. Stainless steel has a lower conductivity than regular carbon steel or galvanized brick ties, and you get the added benefit of additional corrosion protection there. Also, all the major brick tie manufacturers create what they call a thermal tie that incorporates some sort of material separation, isolation between the metal components to either prevent or reduce heat transfer through ties. As we go further, we're going to start getting into the wall assemblies and the results of the NBRC testing. We just wanted to throw out there, go ahead and feel free to put in the question and answer box what your go-to wall assembly is. And keep that in mind as we go through the results. You may be surprised as to which wall assembly performs best. So going back to those temperature cycles that we subject the specimens to, the two sections provide slightly different information. So those static step changes that we do first, that gives us our tested U value, a U vector and R value. It also gives us our tested heat capacity and can also give us a time to equilibrium. Over on our sol air cycle, that is what we use to determine the total amount of energy that reaches the interior. And that's, as we discussed previously, that's our dynamic loading. And that is, that's how we're going to account for the thermal mass within the wall assembly. Here's a matrix of all the wall assemblies that were tested. As you can see, the assemblies with wood backing are slightly different, and that's because that phase of the program was intended for small scale residential, but the wall assemblies are similar enough that we've been able to do some comparisons between those and the other backing types. So here we have tested R value from the hot box in lieu of doing hand calculations. And so as you can see here, we have our dark red brown is our brick veneer, and they actually performed better than most of the other claddings when we use this tested R value compared to a calculated R value. We do have over here in our wood stud backing, our brick veneer is a little bit lower, but it is tested better than one would expect. Also, as we discussed earlier, we talked about that lag between when you have your peak temperature and your peak HVAC usage on the interior compared to when your peak heat load occurs on the exterior of the building. So the lengths of these bars represent the time at which the maximum heat transfer to the interior occurred, and when your HVAC is going to be working the hardest. So as you can see, again, our dark brown brick veneer performed the best out of all the specimens. And since the peak energy was applied at 12:30 in the afternoon, that means all of these examples of brick veneer wall assemblies delayed that peak HVAC usage to off-peak hours, like after a typical office workday or beyond, which is definitely going to significantly reduce the HVAC loads in a commercial building and give you some really good energy savings. Note that the wall where we had brick veneer on CMU with continuous insulation performed the best, delaying that peak energy usage almost until 9 o'clock at night. This graph represents the total energy that passed through each wall and reached the interior during the 24-hour period. These are the results of the sol air phase of the testing. Now, in this case, we flipped our graph upside down, so a shorter bar means less energy use and better performance. So as you can see, in all of these cases, brick veneer, the specimens with brick veneer allowed the least amount of energy to pass through the wall. And we had the most significant reduction in heat transfer between, out of all the wall assemblies, with our steel stud, with continuous insulation and bat, and then also our CMU with continuous insulation and integral insulation. We also had our CMU with continuous insulation not perform too shabby either. Now, in all cases, with the exception of the wood stud backing, in all of these primarily commercial wall assembly, all of that insulation was 2 inches thick. We did not vary that. So really a big chunk of this difference in performance is the presence of the brick veneer and the airspace behind it. This graph is a different way of looking at that total energy usage through the sol air cycle. Again, our short bar equals less energy use and better performance. Here we compared only the brick veneer wall assemblies to a generic reference baseline wall that matched the same sort of backing that was here, like a backing, a wall assembly with the same backing, but essentially no cladding on it. And you could see the savings from just adding the brick veneer range from about 30% to 50%. In addition to the hot box testing, NBRC developed their own climate modeling tool that allowed them to use that research to simulate the performance of brick veneer wall assemblies using real-world weather conditions, where they gathered weather data over an entire year for a variety of different cities. Now, this was a way for them to address kind of the in-between. So in one case, you have R value, which represents the lower end of performance of brick veneer wall assemblies. And then our sol air cycle is our other bracket, where it represents the top end of performance that we can get out of our brick veneer wall assemblies. Actual real life performance is going to fall somewhere in between, because it's going to vary based on where you are and potentially the orientation of the building and variations and things like that. So here we have a table where they use their energy model and the weather data from all of these example cities to evaluate the difference in performance using those commercial wall assemblies that they tested. And they found that the brick veneer with continuous insulation did perform best in all of these locations, and it reduces the amount of energy usage by up to about 25%. So how do we apply this information to projects? You may be surprised that the wall assemblies that perform best in our research are not necessarily the most expensive. So this graph is an illustration of the findings of an analysis we had done by RS Means, the construction cost estimating experts, for the cost per square foot of common commercial wall assemblies. And you can see that the two assemblies here with brick veneer cladding cost less than the average of all of these 7 assemblies tested. And so by using these research findings, it should be obvious that brick veneer wall assemblies can play a significant role in helping you achieve net zero goals. An example of this is this middle school in Maryland, which was featured in as an ASHRAE Award winner and featured in one of their magazine articles. They chose the primary wall assembly for the school was chosen to be brick veneer on CMU with continuous insulation. And what's interesting here is that they backed into that decision. Because it was a net zero project, they first started with the energy requirements and all of the mechanical and electrical, and from that, they knew what kind of performance they needed the envelope to have, and then based on that, they figured out what wall assembly would help get them there. And ultimately, they decided on a masonry wall assembly. So as technology improved, we moved away from thermal benefits that brick masonry can provide, but we want you to reclaim them. So I hope you can see how brick veneer can be used in multiple ways to suit your various project needs. So in some cases, you may be able to qualify as a mass wall. If you're not comfortable with that, you can certainly follow the code requirements for frame walls, but just keep in mind that you'll probably achieve better than expected performance if you do that. And then something that you can actually take advantage of right now is that you can account for the full dynamic performance of brick masonry in your projects that incorporate energy simulation and full building modeling. Most of the high-end whole building modeling software programs do have the capability of incorporating thermal mass benefits. And so as we saw from the middle school example, hopefully those will allow you to achieve net zero goals. So in summary, the NVRC research findings told us a lot of interesting things about brick veneer wall assemblies. So the big takeaway is that we want you to know that R value doesn't tell the full story of energy efficiency, and especially when it comes to wall assemblies that have thermal mass. You need dynamic testing to demonstrate to you the full benefit of that wall assembly. You have the potential to reduce heat transfer 40 to 50%. You're going to your veneer ties are not going to act as thermal bridges. That airspace behavior differs from the assumptions. And so, for these and all of the reasons we discussed, I hope that we've convinced you to put brick veneer and other masonry assemblies on your short list. I do see a question here, and that's the conclusion of our presentation today. Here's my contact information, please, if we're not able to get to questions, or if you think of one later, please feel free to reach out. We're happy to assist. I do see a question asking for the slide with construction costs. So I will go back, put that on the screen. Here you go. Any other questions? I know we threw a lot of information at you. Was any dynamic testing done on traditional historic wall systems such as triple white masonry wall? No, there was not any, that was not one of our specimens that were tested, and primarily because that those type of assemblies would currently fall under the categories for mass walls. So in our case, it was kind of brick veneer falls in that gray area, and there wasn't a lot of information about how they would perform. You may be able to dig in you may be able to find some research on mass masonry walls, because a question that had been asked before, somebody had asked, well, why haven't we heard of this before? And sadly, the answer is this is not new research. This kind of research on thermal mass, even on the, the thermal mass benefits of brick veneer, has been studied for, probably a couple decades. And it just, I think it's like I mentioned when we were discussing R value, it's a little complex, and it didn't, it doesn't fit easily into codes and standards requirements. But it's something that you can take advantage now that we have modeling tools. It's something that's easier to incorporate in your projects. Another question is, I'm in the West where thin brick dominates. Is there any current research on performance criteria? Yes, out west, thin brick is definitely going to dominate because of seismic issues. We do have research that is in progress right now. The MBRC is continuing this hot box research into thin brick wall assemblies. It is not complete yet. It is in progress. They have about 6 different wall specimen types that they are testing. And I don't know if you were able to see from the graph, it may have been a little too small, but each of those stair steps takes almost 2 days for the wall assembly to reach equilibrium. So the specimens are in the hot box for quite a long period of time. And so it's not very fast, but I can promise you that that research is coming in the future. Any other questions or recaps needed? Well, great. Thank you guys so much. Here's my contact information again. Please feel free to reach out with any questions you may have about this topic or anything else brick masonry related.
Thank you so much, Courtney. That was a wonderful presentation. Just so everybody knows, this is the last seminar of Glen-Gery's spring seminar series. So please be on the lookout next January when we launch our new schedule. Like I said before, everybody will be getting their certificate of completion early next week. And if you applied with your AA number, you'll be receiving credit that way as well. Thanks again, Courtney, and I hope everybody has a great day.